Hello, today we are learning about exponential growth and decay functions. I know I've got it when I can model exponential growth and decay. So some key vocabulary: exponential growth, exponential decay, and half-life. A quantity that grows or decays by the same percent at regular time periods is said to have exponential growth or decay. So if it's growth, it's going up from left to right. If it's decay, it's going down from left to right. Now you'll remember that when we did exponential functions, I told you that if the b was greater than 1, it's increasing, and if it's less than 1, it's decreasing. This is the same thing. So modeling exponential growth, you need to pause this and write this down. Y equals c times 1 plus r to the x, where y is the initial amount, 1 plus r is the growth factor, r is the growth rate, and x is the number of time intervals. In 2015, let's suppose a town named Jackson had a population of 15,500 and was consistently increasing by 10% a year. If this yearly increase continues, predict the city's population in 2035. Well, okay. So we're going to plug in what we know. We're predicting what it will have. The initial amount is C. I'm sorry, that should say C. So it had an initial population of 15,500, and it was consistently growing by 10% a year. If this yearly increase continues, predict the city's population in 2035. Well, from 2015 to 2035 is 20 years. So I'm going to put that in exactly like that in my calculator. And when I do, I get 104,276. Now, you actually get 276, let's see, 104,276.24, but you can't have 24 people, so you just end it at 104,276. All right, so decay is the same thing, but it's instead of adding r, you're subtracting r. Well, there we go. Okay, so a large golf club holds single tournaments each year. Golf club holds single tournaments each year. At the start of each tournament for a particular year, there are 512 players. After each round, half the players are eliminated. How many remain after 6 rounds? Okay, so at the beginning, there's 512 players. At the beginning of the year, half, so that would be 50% are eliminated. How many remain after 6 rounds? So if you put that just like that in your calculator, you should get this. So you should get, let's see, let me make that go away. You should get 8. There are 8 people left. All right, this is one for you to do, so go ahead and try it. And you should get 16 players. All right, the half-life of a substance is the amount of time it takes for a half of a substance to decay. So you use the decay formula, where R, the rate, is 50.5 because that's half-life, 50%. So X equals the time intervals. This should be X. X equals the time intervals, years left over the half-life. All right, so let's try this one. So a form of DDT pesticide banned in 1972 has a half-life of approximately 15 years. If a storage unit had 400 pounds of DDT, how much DDT is remaining after 72 years? Okay, So we're going to use the decay formula. So, well, it's a half-life formula, but you use the decay. So C equals 1 minus R to the X, or to the T if you rather. So Y equals C times 1 minus 0.5, because that's the half-life. Okay, so to get X, we take the years left, so after 72 years, and divide that by the half-life, which is approximately 15 years, and you get 4.8. So if they had 400 to begin with, 400 pounds, 1 minus 0.5, and then your half-life, it's the whole years divided by the half-life, you get 4.8. So if I work that out and put this into my calculator, I would get about 14.4. So in 72 years, 14.4 pounds of DGT remains. All right, the next one. A form of nickel has a half-life of 96 years. How much of a 30-gram sample is left after 250 years? So again, to find the X, we say 250 years left, right? Left after 250 years, and it has a half-life of 96. So I get 2.6, and I'm going to plug that into my formula. So C, what was the beginning amount? A 30-gram sample. So remember, it's C times 1 minus R to the T, right? So Y equals 30, 1 minus half, because it's half-life, to the 2.6. So if I do all that in my calculator, I get 4.9. So in 250 years, 4.9 grams of nickel remain. All right, here's one for you to do. Pause it. Okay, so in 500 years, 0.8 grams of uranium will remain. So I know I've got it when I can model exponential growth and decay, but do you really understand? Each time the cells in a sample divide, there are twice as many cells in the sample as there were before the cells divided. Is the function that represents this situation a linear function, an exponential growth function, or an exponential decay function? Explain. The function is an exponential growth function because the number of cells growing by the same percent each time they divide.